Orbifold cohomology, case theory, and the Rham cohomology with possible applications to lambda Ainsworth theory.
Yeah, thank you for inviting me to speak. And see, I didn't provide an abstract because the title was so long. No, actually, I forgot to provide an abstract, but you can take the title as an abstract. It's very descriptive. So I'll just go along the title, as I said. I'll use that as an abstract. So the first thing is sort of what is this global stringy picture? So global orbifolds. So what's a global orbifold for me? It's going to be a pair xg, where G is a finite group. That won't change. And then usually I would say X is a smooth projective variety. On which this G acts. But you could also make this to be X. G could be stably almost complex. And G equivariant. And an example would be if you had a symplectic manifold, which has a G action, so symplectic G manifold. So this is what usually the global is. And just to contrast, I'll say what local means, or in general, just if you just talk about an orbifold. Well, then there are two ways to do this. I mean, sort of you could look at local models, which is not so great. Or basically, you look at the stack, say, of X mod G. And this works. I mean, you don't have to say the word stack, but so there's a geometric way of looking at orbifolds having just local charts which are a finite group acting on space and so on, and then you get some topological space. Yeah, exactly. Yeah, but then it's a much better idea to talk about about groupoids, and then if you're talking about groupoids, you're sort of in stack land. And then everything becomes much more difficult, or a little more difficult depending on your point of view, because there is a categorical shift, right? I mean, here I'm still talking nicely about spaces. Somehow if you look at this, then actually these guys are one categories, and then you have to wonder about what the maps are and so on and so on. And strangely enough, the global ones serve as a local model for the non-global ones. So basically what you can do for the global ones, you can do for anything. So what's the idea? So the idea is that the geometry of this pair xg is the geometry, or actually maybe the stringy geometry of the following thing. Let me write it as I of x and g, so the inertia, and I'm talking about the inertia variety, which is just the disjoint union over all elements in the group, fixed point sets under this g. So usually we call this the inertia variety. If you were in stack land, you could actually produce the inertia stack here. So if this is x, and if x is suitably nice, say the linear Mumford, you could look at the inertia stack there, but that's a huge gadget. This is much smaller. If you want, I can give you an example, but maybe I can do this example here. So I mean, the simplest example, which is always fun to keep in mind, is you take a point with a g action. Then if you look at this I of point in g, then this would be just the disjoint union over group elements, G and G. And you have, the fixed point is just this point, so you would have point here. But if you would do this bigger thing, so I of point mod G, what you would get out is you would get the direct sum over conjugacy classes in G. So conjugacy classes. And then here you would get the point mod the centralizer of G. And this is again a stack. So you'd sort of be talking about things like this. But today I'll just do this because, as I said, sort of this serves as a model for these things. So what I mean is, so what, how to think about this. So maybe, so let me call this a precursor, is the following theorem by Atiyah and Siegel. When was this? 89. So if M was smooth manifold with a G action, with a smooth G action, then the equivariant K theory of X is equal to the direct sum over the conjugacy classes. Oh, I should tensor with C here. Conjugacy classes, so then you take the K theory of the fixed point set, tensor with C, and take the ZG invariance of this. And notice that this is direct sum over G and G. K of xg tensor C. And now take the G invariance of all these things. So one thing you should see here, this guy has a G action, which sends xg to xg hg h minus 1.
What's ZG or what?
Oh, ZG is the centralizer. ZG is the centralizer of G. So this is kind of an indicator that you look at this. And why did they look at this? So this is even before you had digraph Verlindness. They sort of had a stringy motivation for these. So they introduced stringy Euler characteristic. And this was sort of an answer to get a mathematical theory or model for getting the stringy Euler characteristic. So now, yeah, and so in principle there's this physics slogan: the string smooths out the singularity, and the idea is that this inertia variety actually is where the string is supposed to live. It has these twisted sectors, so the components are sometimes called twisted sectors, and it has these components which take care of this. And let me define one thing, and I can get back to that. So that f be now a functor, which is either a K-theory functor, so I'll have K0 or topological K-theory, or it's a homology type functor. You could take Chow theory, or you could take cohomology theory. And it doesn't matter. I mean, you can see that, well, in this situation, you can actually use topological K theory. Then the other one, you probably use K0 and A. And then H star, you can use as you wish for both situations. And now you just say sort of the stringy version, so F stringy of this pair X and G is just by definition F applied to I of G. So this fixes I of X and G. So this fixes the additive structure. And you can see this fits well with this guy. So what I'm sort of doing is I'm using this guy. I'm not going over C coefficients, but I'm just using this guy, and then it has a G action, and I'm free to take G invariance or not. Okay? Certainly, if I look at the bigger thing, I will know what the G invariants are because I retain the G action on this. So this guy still has a G action. So you keep that. This still has. And one thing, this is my personal belief: avoid taking G invariance until the very last minute. So do the constructions before taking G invariance, and then at the last, if you want something, at the end take the G invariance. Okay, so this fixes the additive structure. So the stringy part is sort of the multiplicative structure. So the stringy part is the multiplicative structure. So, and how do you write down this multiplicative structure? Maybe I should. So, what does this mean? So, did I mess this up? Yeah, I should have probably taken the other one. I never know. Okay, so what's the idea? Is you want multiplication that looks like this of complex. I should have said compact here. You'll see in a second why.
Well, you assume that the f already has a multiplication.
No. I will use that somehow. So this is, but that's a very good comment. Thank you very much. So you already see here, this thing here, I mean, all these f's have a multiplication. They're all, these functors give you rings, the 4. Then this guy would have a ring structure, which I call the diagonal or naive ring structure. Because this is a direct sum. I mean, you can see that this is the direct sum over the g, and then it's just f of xg.
No,
and all these guys are rings, and there is a ring structure here. But that's not the one I'm looking for. That's not what you want.
But you still need to have a functor f which has a multiplicative structure.
Yes, to work this out. Yes, exactly. Exactly, yeah. You'll see this in a second. But it's not the naive one you would want to do. So this is somehow, this should be G graded, and again you can get this from a physics thing. So maybe I write this here as a physics motivation, because I'll get back to this. So physics motivation. And sort of, the physicists write some formulas which include so-called twist fields. And then if they have this situation, so they have, a finite gauge, finite gauge group or finite, it's a gauge group more or less, gauge group G, then they sort of have twist fields. They call psi G, this is sort of a twist field. And then they write things like this, 3-point functions of some phi 1 psi G1, phi 2 psi G2, phi 3 psi G3. And, this is something, and then this is 0 unless G1, G2, G3 is the identity. So and then they sort of, maybe I should put commas here. So it's of course very hard to actually figure out what this is. And then they always say they can do this, but I only found one paper in the 80s, and I forgot to look up the reference where they did it actually for twist 1/2 fields. So there is no mathematical theory which ever sort of substantiated this, that you can do this. But you can see that if you have 3-point functions like this, you can dualize them, you get a multiplication. Since they multiply to 1, then you exactly get a G-grade multiplication. So this is the thing. So how would you get this? So maybe I'll put this here. And if you think about it, so what happens is, well, you have x and you have the fixed point, the 3 fixed point sets sitting in here. And they all sit in here. And you could look at the common fixed point set, so xg h. So I'll use this sometimes. So angular brackets mean the group generated by the elements that are in there. So, and you have 3 maps here. And if I'm really careful, I have another map here to x gh minus 1. This is just because I'm being overly careful. So sometimes I will maybe by habit make these things known. So there are these 3. So this map is actually just the identity. So there it means nothing, but in here there are different components. So it actually switches 2 of these components on that space. So if I put a check over it, it means that I'm going to the gh minus 1 component. Of course, what's fixed by gh is the same thing fixed by gh minus 1. So maybe actually, so let me drop, so that's the disclaimer. So if you want to read the paper, we'll always work with E3 check instead of E3. But now, just to make the formulas nicer, I'll just directly go to gh minus 1. Okay, so there are 2 ways. So basically, so looking at this diagram, you would see basically two ways of getting this multiplication going. So the first way would be sort of to use this bottom diagram, and I'll talk about that first. And the second one would be sort of to try to use this. And as correctly remarked, I mean, somehow these are functors that have a ring structure. So what do I mean by using the bottom diagram? So the first thing, so let's call this 1 and 2. So 1 would be the formula where you first pull back and then you push forward. Namely, the idea would be, well, I have these things, so if I have some class A in f of xg, I should put this here, so space element f of xg and B in f of xh, then what you would try to do is you could pull back this class A, pull back the class B, then realize that down here I can apply the functor and it has a multiplication, so use the multiplication, and then push it forward to go to here. And this is why I needed compact, because, I mean, in K-theory you have push forwards anyway, but in, of course, in cohomology you don't have so much of a push forward. You have one in homology, but you can use Poincare duality and then use that as a push forward. So this is why you need compact. And it turns out, well, you should, well, this would give you, without anything here, this would certainly give you a map, but this wouldn't, and would give you a multiplication, so a bilinear map, but this multiplication wouldn't be associative. So the point is that what you need to add some obstruction here. So let me call it obstruction GH. And then, so need this obstruction GH to make the multiplication associative, make it associative. So what is this obstruction class? And see, you know, the title had these many words. Really, the funny thing is that it doesn't care very much about this functor, which is a great thing about this construction. So the idea is, what I need the following notation. I'll take the Euler class of some bundle E to be the top Chern class of E if I'm in A or in H, and I take it to be lambda minus 1 of E if I'm in K theory. Then this obstruction here, so then the obstruction GH, this is just the Euler class of some obstruction bundle R of G and H, where R of G and H is equal to the following thing. So it's SG restricted to XGH, it's probably off, plus SH restricted to XGH plus SGH minus 1 restricted to XGH minus the normal bundle of X. And I probably got this wrong anyway. So what do you want to say? Sorry, the normal minus the normal bundle of XGH, I think. Yes. In X. All right, so this is, and now I need to tell you what these bundles S are. So what are these bundles S? This is the whole story. So these bundles S encode exactly this thing. So let's look at the following thing. If I look at Tx and restrict it to Xg, this has an action by cyclic group generated by G. And then I can break this down into its eigenbundles. So direct sum over the W and G K. sum over k, where on WGK, G acts with eigenvalue e to the pi I k over the order of this element G. And this is where I need my almost complex structure. I have the cyclic group. It's an abelian group then, and then if I have an almost complex structure, I can diagonalize this action, and then I can do this component-wise if you want, or something like this. So I look at each xg, I have this action. Then since xg itself is fixed, it acts on the fibers, I can decompose the fibers and look at these fibers move. And then I can, and now comes the trick. So this is the sort of the magic formula. So what is SG? So this is the sum over the k over the degree, so the order of G, W, GK. And this is an element in rational K theory of X. So I'm more or less morally taking roots of these things, corresponding to the log of the eigenvalues. So this story is very much a story about log of eigenvalues. So you have these eigenvalues and you want to get this factor out. So here I'm sort of morally taking the, so one has to be a little careful. So k equals 0 to r minus 1. And then maybe the remark about stable one can make here. So of course if I start at k equals 0, so that's just the tangent bundle of xg. Namely those where it's fixed. So I could start at k equals 1 because there's no contribution here. So basically I'm just looking at the normal bundle of these things. And then when I go to stably almost complex, all these things are about normal bundles. So if I start stabilizing, I'm just adding trivial representations and they don't play a role here. So nothing happens then. So this is the thing. So now we have the theorem. So this is joint work with Tyler Jarvis and Takashi Kimura. So so this obstruction gives f of Ig the structure of G Frobenius algebra, and there is a Chern character, and furthermore, so the construction passes to I of X also with a Chern character. So there is some, I mean, this is, as I said, you use this as a local formula. You have to be a little bit careful because the inertia stack is not quite just the inertia variety, but the sort of the morphisms and the yoga carries over, and then you can make this even work for the global thing. So now, what's the G Frobenius algebra? Well, it's that's a long story. I sort of Turayev and probably invented this first, and then some things changed. I also wrote down an equation, and it's so depending on how algebraic you are. So the first definitions are sort of 4 pieces of data and 10 axioms. So I'm not going to write this down. And then there is an easy to remember definition, which is the following. So, but then it uses a little bit more category theory. G Frobenius algebra is an algebra object in the category of DKG modules satisfying 2 axioms. So KG is the group ring, is a group algebra, yeah. And this is the Drinfeld double. So the group algebra happens to be a Hopf algebra. And then there is a construction for Hopf algebras to make another Hopf algebra out of it, which is linearly basically twice this thing. So the thing tensors itself. It's called the Drinfeld double. I can, if you want, I can write it down. And then you take an then this has a category of modules. You take an algebra object in there and have 2 more axioms. So, and this is, well, I mean, this characterization was done together with one of my students, David Pham. And what this means in particular, well, I mean, these are, as I said, there are certain axioms, and I don't want to go through all of them, but one thing it means is it's G-graded and has this G-graded multiplication, and it has a G action, and the G action acts by conjugation on the graded pieces. So those are things that make it into a G module. And then there's one more thing you could ask yourself, which nobody asked, and this thing is associative, but is it commutative? So the answer is, of course, no, because it's G-graded. If G is not an abelian group, this thingy is not commutative. Well, there's a next best thing. It's sort of braided commutative, which is built into this these modules. That category is a braided monoidal category, so you actually know how to switch things around. You have to take the G action, so that's also encoded in these words. Then if you go to G invariance, then actually if you go to G invariance, you can figure out, because of the G braided thing, it's actually commutative. So this is kind of nice. All right, so there's this whole structure plus, and I sometimes like to stress this and sometimes not. There are two axioms here, which are, one of them is really not obvious. Again, I don't want to write it down today, but it's a trace axiom. It's a trace of some G action. On one sector is the trace of some other G action on some other sector, which is, this does not really have to be true, except from physics points of view, because it's a genus 1 correlation function. It's a factorization of a genus 1 correlation function, and then it has to be true. And it's and this actually works out for this guy. If we computed it, that this works out for this guy as well. So let me get a little bit of the history. So what this generalizes or does. So let's see what was known and what wasn't known before we did this. So in principle, you have, so for this H star of X, and this is not so bad. The stack is not so much different than this guy if you're using H. It's very much different if you're using K. Sorry, the inertia variety and the inertia stack, if you apply homology to it, there's not so much difference. If you apply K-theory to it, there's a lot of difference, and you can actually see this here, because if I'm going to take K-theory here in the stack sense, those will be ZG equivariant K-theory. I could have taken X. But if I take the ZG equivariant homology, I just get the homology of the fixed point set. I forget about this G action. So most of the complications go away there. So this was done by Chen and Rham. So what was it? So they have a paper in 02, and we did it in 04, and then you had H star of this global quotient that's sometimes known as a Fantecchi-Göttcher ring. And when did they do it? 03. And I didn't mention this, but in a sense what this is these are the rudiments of a Gromov-Witten theory of orbifolds. So this is a genus 0, beta equals 1, 3-point orbifold Gromov-Witten invariance. This is what they are. And so if you distill this, you get this new classical structure, which they did. Then Bauer and Lothar, they figured out how to use Galois covers to get the same ring structure. And then with Tyler Jarvis and Takashi Kimura, we proved that if you can set up a G equivariant Gromov-Witten theory, G cohomological field theory. So you do everything you know from Kontsevich-Manin for Gromov-Witten invariance cohomological field theories, and you put a G in front of everything. That actually works. You have to define the stacks and so on and so on, and then these 3-point functions actually become this multiplication. So
projective case.
In
So who did that in general?
What?
I mean, this Gromov-Witten invariance.
For orbifolds? Well, in principle, Chen and Rham did this, although the paper is still outstanding a bit. I mean, there is a version in something, and then Abramovich, Graber, and Vistoli looked at this again very carefully, and then this paper exists now in two versions. There was a announcement version, and then one with all the details.
And what is precisely the setup?
So for the symplectic thing, it's subtle to get the right. So I'm not an expert, so I shouldn't say much, especially if I'm on tape. No, it's subtle to define the spaces and the maps and the pullbacks and so on. This.
For the Gromov-Witten theory in the symplectic case without groups, so in all the papers which exist, so whenever somebody looks at this, they find mistakes and so on.
Yeah, it's tough. It's subtle. Yeah, it depends on some things.
G case could be much better.
Maybe the group will.
Yeah, maybe the G.
That would be one hope.
So I'm on the safe side on this fence because we use the algebraic setup and use the algebraic moduli spaces where these, the problem is constructing these fundamental classes, and then you have the Vera and Fontecchi way of constructing fundamental classes, and then you have them on this moduli space, and then we used admissible G covers, and then you just have to lift something from one stack to another, and you can actually do the calculations. So things are well defined. It's not clear that you can actually calculate them, but they're well defined. So, and as I already said, so for the showering, this was, so these things were, so actually probably the showering of X. This was done by Abramovich, Grama, and Vistoli, and I still have the O2, but I think there's a more recent paper with more details that just came out. And then for K-theory and topological K-theory, this was actually another paper of my collaborators and myself in 07. So and this one has the first, so this formula is from this paper. And the good thing about this formula is that, where's the formula? Where did it go? There it is. This formula is from this paper. So previously you have this obstruction class which you get back from pulling back curves or something like this. I mean, it's just the usual thing. I can write it down for you. It's an R-1 of something. But this is a sort of, this is a combinatorial version. And before, see, now you can do it for stably almost complex. Of course, I mean, mapping curves into something stably almost complex is not such a good idea, because you wouldn't know what you're meaning by this. But here it actually works out, because so in this classical limit where G is equal to 0, you just get a formula which has this group action in it. So in that sense, it actually gets to be nicer. Right, and then, so now with that, now I have a definition, and again, you can again see that, but maybe you all know this, so then I'm saying something you know. So I had this on the board that this geometry is the geometry of this inertia, and now this one I still need. So the standard example people take is this Kreppen resolution conjecture. So Ruan's Kreppen resolution conjecture. So in principle, what this says is, you could look at the quotient of X mod G, say, and you look at the, you could look at some resolution of this. This should be Kreppent. And then the idea is that you guess that, so this is just rudimentary, that K of Y is isomorphic to this K of X and G. You have to be a little bit careful. This is very coarse. I mean, first of all, this is not enough. You have to put more. I mean, the first one was like this. Now you have to put more things like this on, more restriction on it. And then you have to be a little bit careful because, so somehow, well.
What do you mean by the first one was like this?
Well, I mean, there's several of these conjectures. They sort of they evolve over time. It's a conjecture with a time parameter. There is a flow of this conjecture to more and more trees. This I don't know. I mean, but there is a famous example. So that this, instead of saying the conjecture, but people love saying this conjecture. But here's a nice theorem, which is more or less I think it's due to Lehn and Zaga. I'll attribute it to them. Which is, if you take the following things, what you could do is you take a K3 surface. I can tell you a little bit more about this anyway. I mean, the thing is that, this is known for threefolds. There's this Bridget King-Reed paper, which uses G. Hilbert schemes to actually do this, but not the full multiplicative structure, but the additive structure. I mean, there are some things that are known. So, and then if Z is a K3 surface, you could look at the symmetric product of Z.
What are the names, sorry, on the blackboard?
Lehn and Zaga. Manfred Lehn.
S-O-R-G-E-R?
Yeah.
Ah, okay.
Maybe it's Serge.
No, I mean, it's Austrian, I think.
No, it's Zaga, but I think he's in France, right? Yeah, that's why I'm saying Serge. I think so. You could take so this is another nice example I could have mentioned, which I really enjoy doing is, so point mod G is a great example. Another great example is you take whatever you want and you take its nth cross product, and that has an action of Sn on it. So that's another example. So you could take Z cross n and then mod out by Sn, that's singular. And then you could look at the Hilbert scheme of this guy. And that's a Krepin resolution, and then this is true. So which is, again, I mean, this is a really non-trivial statement. And additively, you have this Bridge and King-Reed results. So somehow this is some motivation why you may want to study this geometry. All right, so this is how this works. Now, you could do the other thing. And actually, for me personally, my first approach was actually to use the easier one instead of going to this double intersections, just pushing forward. So you could try too, namely using this guy and try to write down some formula, and I put this in quotes because you have to be very careful. You could try something I3 pullback, I3, I1 push forward of A, I2 push forward of B, and then something here. Yeah, I don't know what to call it, called big gamma of GH. And you could try something like this. And it turns out that this is not, so you're going to have a little bit of a problem here if you're starting using push forwards, because of the following thing of the projection formula. If you push something forward and pull it back, you're going to get an Euler class. So if you do this, somehow you're going to get much too many factors of Euler classes that you actually didn't want. Okay? So the thing is, so this is you get, let me write too many Euler classes, and you'll see these coming up in a second. And the problem, of course, is, and this is a serious problem, when you get these Euler classes, you kind of want to take away these Euler classes, but then you would have to divide by them. But there is no mathematical construction which lets you divide by something in a nilpotent ring by dividing by nilpotents. You can localize, but then you get 0. Yes, you smile. Some people did this. I mean, you can sort of write. I'll do some things like this and say formulas and quotation marks. And if that makes you feel uneasy, I'll give away the end. You can do a construction. I proved that you can do a ring extension and a construction where you don't have to use these symbols that are never well defined. Okay, so you get too many Euler classes, so you kind of have to divide out by them. So, but it does work. So it does work. So this works if these I pullbacks are surjective. Because then instead of using push forwards, then you can use sections. IS, so that, I pullback of IS of A is A. And you can try to go for a formula like this. So you can look at I3 pullback of I1S of A times I2S of B times some cocycle gamma GH. And now this actually works. So this works. For the following things, what I call special G Frobenius algebras. And this only means that basically this means that f of xg is cyclic, is a cyclic module over f of x. So this is less of the structure, so you always have pullbacks in these things. So then you can use this naive multiplication. You pull back something from f of x to f of xg, and you multiply an xg. That's the module structure, and that doesn't get changed. This is one of the ingredients of the theory that you try to write down this multiplication, but the module structure over this identity sector should not be changed. And then it's then these gamma GHs, there is some sort of cocycle. And you can try to solve this. And actually another thing which is kind of interesting in this approach is that no one actually says that you can only have one such cocycle. In principle, one thing where you can see this co-cycle approach is directly that you can always twist by something that's called discrete torsion. So if you have one multiplication, you can twist it by a second group cohomology element of this group G and get another multiplication that again gives you this algebraic structure of G Frobenius algebra that one is after. So what's the theorem here? So the theorem here is sort of, well, I mean, it could actually be, the way I phrase it is that there is no solution, right? You want to write this down, maybe there is no such co-cycle. And then, so the theorem here is that, let's see, did I write this down? Is that, so in the situation above, gamma GH.
In general, there are more solutions to this. So
I actually think so. Let me comment on this. So let me just write down this formula. So if you have this, and then you can use these pullbacks, you can actually calculate that, this I3S of this push forward of this class is this guy. And I'll say something more. So that's actually a good question. So in maybe, was it 04 or something? So in 04, I looked at sort of just these kind of quotients and asked myself this co-cycle question, because in these kind of quotients, they are cyclic. And then you can do a computation, which is unfortunately a long computation, but you figure out there is at most one. And then if it's geometric, namely it's really x to the n. So I looked at Sn Frobenius algebras, and then there's with some condition like this, namely that the sectors are cyclic, then there's at most one. And in this case, it's unique up to discrete torsion. So you can figure out that you can solve this equation, you get two solutions, and this has something to do with that there is an element in H2 of Sn with, let's see, with what coefficients? It's probably the one coefficients.
in general, what's the feeling?
And in general, I have the feeling that this is actually a special solution, but it always exists. So that's my general feeling, that there could be more of these guys out there, but this one is particularly nice. And here's another thing. This is why I still thought about this even after having the solution is, well, I mean, somebody said, how do you? I forgot. It was a smart person that I asked because I said I have a co-cycle, and he says, you know how you get a co-cycle. Any co-cycle is trivial. In the sense that it's very hard to write down something that's a co-cycle unless you know that it's a trivial co-cycle. That's the boundary of something. So the idea is, and I'll put a formula in quote. Actually, in this case, the formula in quotes is like this. It's I1s of fractional Euler class of SG, I2s fractional Euler class of SH, and over. So this is why I have to put this in quotes, because it doesn't quite work this way. But this is what it is morally. So this is a moral equation instead of an amoral equation. So you'd want this thing to be somehow, I mean, it could. So you ask me, how do you solve this equation? And this is really maybe, yeah. So maybe I'll solve this. So I'll state it as a theorem. There is a ring extension. And this is always actually such that the pullbacks become such that the I star are surjective and the co-cycles become trivial. So you can work out, I mean, it doesn't work directly on the original rings, but it's somehow, there are two extensions. One is giving you these kind of fractional Euler classes. I wrote them in Frakturschrift to stress fractional. But the idea is that, well, I mean, so what's the idea? So let me maybe write down one formula, which is already a true formula, and then you can see what the aim is, and then the rest is just some technical construction. But the aim is the following thing, namely, if you would, instead of using Euler classes, you had used total Chern character. then you could have figured out, so let OIT be either the total Chern class or lambda minus lambda sub t for those different theories. Then you could have figured out that A star B is actually, so the evaluation, or I would have to say what the evaluation is. So the evaluation of some E, this is either, set T equals to R if R is rank E, so of OIT of E. So T equals to R, or you just set T equals to -1 in the other case. So so you have eval T equals to R. So sorry. Of I3 pullback of I1S of A Euler class T of S of G, I2S Euler class T of S of H, and then some strange term which is, sorry, I3S, this is not the strange term, Euler class T of S of GH, and then some strange term which is E3 push forward of the Euler class T of the negative normal bundle of X GH. So if you do this, and then you should, then the point is that these classes are not multiplicative, these are. So if you look at this direct sum decomposition that I had for this original formula, there were these factors k over r, which sort of would give you roots of these things, and you can write them out, and you would have something like this. The problem is in this formula you can pull it out, but then you can't evaluate at t equals something if these guys aren't bundles, because it doesn't make any sense. Because you wouldn't know what the rank of these guys is, because it just doesn't make any sense. And this lambda -1 series is also not so good. So you'd have to sort of reassemble it until you get a bundle, and then you're back to your old formula. So what I mean by these ring extensions is that you sort of can extend stuff by taking fractional Euler classes. That's just like the usual trick with splitting manifolds that Hirzebruch used to do. So I forgot what it's a splitting manifold, right? I mean, to get virtual line bundles. So here you sort of take roots of these line bundles. So that's not so, yeah. So it can be split. That's a splitting, yeah, exactly. Pulled apart into line bundles, and before you have virtual line bundles, and here you can take the same thing. You sort of formally add roots to these things, and then you have to do it on the bundle side. So there you're talking about a monoid, you extend that, and then on the other side you extend by roots. And then what gets tricky is that you're dealing with these guys, and so here it gets to be a little bit more difficult because those, Euler class of minus something, this is one over the Euler class of something, but one over the Euler class doesn't make any sense. So the idea of how to treat these guys is exactly that you get these formal sections. So that actually works out, and then there's some formal mathematical argument. So this works out nicely, and so now I have this thing. And why would I want this? Well, I mean, for 2 or 3 reasons. So I have 10 minutes, so actually I can get to the Rham part and maybe a bit about to this Landau-Ginzburg part. So what about the Rham theory? So there was a paper by Chen and Hu, which I took as inspiration. So Chen and Hu, they looked at the Rham theory for G abelian, and sort of used this form 2, this form 1, where they use push forwards here. No, that's a good question actually. I think not, but no, this I should be sure.
So when was it?
06. And they're all students of Rouen, so. So that is correct. So they did this, and then they used sort of this setup, and what are you going to do? And so here's the interesting thing. So here the point was that this works if this pullback is surjective. So you could either play in algebraics like I did, and do ring extensions, or you could say you're a geometer, and then you go to the form level, and then on forms certainly the restriction is surjective, right? Why? Because I can take a tubular neighborhood, take some Bank function, I can pull back this thing. right? And I have. So how do these calculations work? What do they need? They need push forward, pull back, Euler classes. Euler classes should be commute with pullback, and you need excess intersection and projection formula. So now you think about this for forms, and there is push forward because these guys are just closed embeddings, and you can look at their normal bundle and take Tom push forwards. So in general you wouldn't have this, but you can take Tom push forwards more or less, and then there are pullbacks. That's no problem, and you can prove the projection formula holds up to a closed form. And also the excess intersection formula that follows from work by Quillen, who did this for cobordisms, that it will also work for on homology, on cohomology, and then you can lift it to the form level, and you know you're only off by a closed form. So then you can use, so with that argument, you can actually do the Rham theory for part 2, just putting it back to the double intersections. And this will work out fine. And then the question is, but Shen Hu tried to do this here, and more or less what they tried to do was assemble this guy and use this formula. And they have some formalism which they write down how to cancel these things. And one of my motivations was to put this into a framework where you can actually, these formulas make sense. They more or less write the formulas of this type. And so this works out fine here. And the idea is, well, I mean, you shouldn't have done a Tom push forward. As I said, you get too much of a normal bundle, because if you do Tom push forward, you pull back the Tom class, you get the Euler class of the normal bundle. Yeah, but what is Tom push forward? You extend you multiply the form by some function, and then wedge it with a Tom form. So just don't wedge with the Tom form. And this is a wonderful section of the pullback, right? Because you're not adding the degree. So the joke is that instead of wedging on the Tom form right away, you do it in this gamma step here, because you don't want to push two things forward. Then on the overlap, you would have too many dx's, right? You write the Tom form locally as dx, whatever in the normal coordinates, and you take the second one, and you get all these coordinates where on the intersection twice. You don't want to do that. So you just use the bump functions, push it forward, and then calculate exactly which normal things you're supposed to have left. This is exactly what this does, and then pull that back. So that's the trick. So this works nicely there. And so the other theorem here now would be that it works for the Rham. So this works 1 and 2 work for the Rham. And not only for G abelian, but just for any G. And moreover, sort of you can make sense of this. So Shen Hu, I mean, it's very inspiring. They wrote about fractional Tom forms. These fractional Euler class of SG, if you do this ring extension for 1, they exactly give you a correct definition of what a fractional Tom form should be. Right, so maybe just 1 or 5 minutes about these Landau-Ginzburg theories. So this is the first thing, and the second one is this, and that's something I'm also currently thinking about. So this is somehow, this is part of this mirror symmetry story about Calabi-Yau, Landau-Ginzburg correspondence, and so on and so on. So the easiest local model, easiest small model is you have a function Cn f to c, and say this has an isolated critical point at 0. And say you have a group action G on Cn, linear group action, so G sitting in G and C, such that the pullback of f is f. So G is invariant. And then you can sort of play the same type of deal with this G Frobenius algebras. Namely, so you sort of kind of want to take a different functor. So instead of taking, what should you take? The idea is that in this case, then f is the Milnor ring. So what happens is you can look at the following thing. So maybe I should, write this. So instead of f of x, you'll have the Milnor ring of this function f. Instead of fxg fixed points, what you have is m of f restricted to the fixed point set of g. This actually works out nicely. So now the question is, So, and when I initially set up this gamma thing, this is actually, it's pretty clear that pullback is giving just by setting some variables to 0. And because this is just the ambient space, you're just restricting the variables. So you have a linear action on Cn. The fixed points of this linear action give you some linear subspace, and then you change coordinates to normal coordinates. And those coordinates, you set the normal coordinates to 0, you get a new function. So there's certainly pullback, and then push forward is also, the section is also clear. You just take a function of some variables and think of it as a function of more variables. End of story. And then you can try to compute these gammas, and then again there is an answer. So this is, so these gammas, they are again unique in lots of cases. So if you look at some older theorem where I proved that, sort of in the ADE and D and F singularities, boundary singularities, there is a unique, but always up to discrete torsion. Solution of this cocycle equation. And this is kind of nice, and then you can use this to get the mirror symmetry MS on the undeformed level. For ADE. And some other pairs. I mean, I don't want to go into the details, but you can just write this down. There's an A model you can write down. There's a B model you can write down. You can actually look at the invariance and get this. It's just a long-range computation. But I wanted sort of, instead of solving this cocycle equation, I was thinking, then now since, we have the solution of this problem by that thing, why don't we try this? And so there's a question now how to do that. Namely, I would need to know what the Euler classes are. And so, yeah, I should say that. Clock stop in 2 minutes. So here's a rough idea, which sometimes works, and you have to put a little bit more work into it to see what actually the correct conditions are. But roughly, what you want to be doing is, if I can find it here. So the idea is if you have some V sitting in GLN, and this is a G subrepresentation, you want to assign that as a total Euler class to be the sum over the lambda I det of Hess of F restricted to V t to the I. So you have the Hessian of this function. And then it's kind of well known for these singularities that the Hessian actually gives you, there is Poincare duality for these rings. And the top dimensional guy giving you Poincare duality is the Hessian of the function. So that serves as the Euler class, which is, for a manifold, you'd get the Euler class as this thing doing this for you. And and then this is just sort of mimicking Chern-Weil theory. So I know what the highest one is. It should be the Hessian on this guy. And then taking exterior products of this thing, then should give me exactly the right. Sorry, I messed up the determinant. Right, it should be the determinant of. How about that? Less frowns, maybe. So you have this guy, and then so you could try to work this out if you sort of use these formulas and for the Euler classes and for these RMs, because those are just SM as a representation of G, and this makes sense here because it's just this restriction of this representation, and figure out how this goes. And it kind of does work for the quintic, so you can try this for the quintic. And you kind of get a strange. This is some weird thing. So if you do this for the quintic, what happens is you get a very strange multiplication. So you use this Calabi-Yau-Landau-Ginzburg correspondence for the quintic, and then we kind of all know for the A model what we should get. So those should be the Gromov-Witten invariants for the quintic, and it's just undeformed things. You should get just this usual thing: 1, 1, 101, 1, 101, 1. 1, 1, 1. So this is the usual quintic, and then you should have the mirror dual, which is this Landau-Ginzburg theory that you compute, and you can actually compute that it sort of has the right there's a bigrading, which I didn't mention, and has this kind of thing. So the twisted sectors here are these guys, and here usually you take the middle dimensional homology. But the funny thing is that these twisted sectors get a multiplication by this guy, which respects sort of the twists, but which doesn't respect the bigrading. So there is some weird thing. So this behaves, so it sort of breaks down into two pieces, and this piece looks like B part, and this part looks like A part, and I still don't know what this is. So I asked Yuri Manin about it, and he said that's Yuri Manin, and he said, yeah, that's for him this was not even a thing to think about because he thinks these things should be motivic and split apart anyway. But I found that kind of interesting that you have this canonical choice of multiplication, and you would get something that you might not expect. All right, stop there with the possible applications.